Okay, in Unit 3, we are going to start looking at solutions to equations with two variables in them. Remember that a solution is what makes an equation true. So we're going to look at the point 0, 3. Remember what that means. That means that x is 0 and y is 3. And we're going to see if that makes the equation y equals 2x minus 3 true. So we're going to replace y with -3, and we'll replace x with 0. And then we will see if that's true. That's a little question mark that I put over my equals sign. Okay, let's simplify each side. The left side is -3, and the right side is 2 times 0, which is 0 minus 3. 0 minus 3 is -3. So yes, that is true, and the answer is yes. That ordered pair makes the equation true. Let's test another ordered pair. So we'll test an ordered pair where x is 1 and y is 2. So I'll replace y with 2 and x with 1. And then we'll do the arithmetic. 2 is equal to 2 minus 3. 2 is equal to -1. That's not true. So the answer is no. 1, 2 is not a solution to that equation. Now what I want you to notice is if I graph each of these points, the point 0, 3, which was a solution, is on the line given by y equals 2x minus 3, and the point 1, 2, which was not a solution, is not on the line. So whenever we graph a line, each point on the graph of a line represents a solution to a linear equation. Linear just refers to the fact that its graph is a line. A system of equations is two or more equations with two or more variables in them. A solution to this system of equations is an ordered pair that makes both equations true. When I say both, that implies that we only have a system of equations with two equations. That's the kind that we're going to look at. You'll study systems of equations with three equations and three variables in Algebra 2. So, in example 1, there are two lines that are graphed for us. The first line is 3x minus y is equal to 5. And that is that graph right there. The second line is x plus 2y is equal to 4. And what you notice is that the two lines have something in common. They both share the point 2, 1. We're going to show that that ordered pair is a solution to the system of equations. That means it has to work in both equations. So let's test the equation 3x minus y is equal to 5 first. So if we replace the x value with 2 and the y value with 1, 3 times 2 is 6, minus 1 is 5. That's true. And so that ordered pair is a solution to the first equation. Now let's test it in the second equation. X plus 2y is equal to 4. So we'll replace the x value with 2, and we'll replace the y value with 1. So that gives us 2 plus 2 is equal to 4. That's also true. So we've just shown that the ordered pair 2, 1 is a solution to both equations and therefore to the system of equations. In example 2, we have another 2 lines that are graphed. The first line is 2x minus y is equal to 1. The second line is x plus y is equal to 5. What we'll notice about those two graphs is that they share the point 2, 3. We can show that that ordered pair is a solution to the system of equations by replacing x and y with 2 and 3 in both equations. So equation number 1 is 2x minus y is equal to 1. So I'll replace the x with 2, and I'll replace the y with 3. 2 times 2 is 4. 4 minus 3 is 1, so that point is a solution to the first equation. Our second equation is x plus y is equal to 5. So if I replace the x value with 2 and the y value with 3, we get 2 plus 3 is equal to 5, which is true. So the ordered pair is a solution to both equations and therefore a solution to the system of equations. If I want to solve a system by graphing, all I need to do is to, number 1, graph both equations in the same coordinate plane. Number 2, write the coordinates of the intersection point. That's where the two lines cross. And then number 3, check the solution in both equations. If it does not check, the graphs may not be correct. Okay, in A, we have two equations. We have x minus 2y is equal to negative 2. Sometimes it's easiest to graph these equations if we solve them for y. That is to put it in y equals mx plus b form. So I'll subtract x from both sides. And then divide both sides by negative 2. And that gives us y is equal to positive 1/2, since negative 1 divided by negative 2 is positive 1/2, times x plus 1, since negative 2 divided by negative 2 is positive 1. Since we have it in y equals mx plus b form, we can now graph it by using the y-intercept and the slope to graph as many points as we can accurately. Accuracy is of extreme importance here, since we want to find the exact point where the two lines cross. Now we have our second equation, x plus y is equal to 4. If I subtract x from both sides, then we can solve the equation for y. Y equals negative x plus 4. If I want to graph this line, then we have a y-intercept of 4 and a slope of negative 1. For a slope of negative 1, the rise is negative 1 and the run is 1. So that's going to be down 1, right 1, down 1, right 1, etc. And we want to graph as many points as we can to have the greatest accuracy. It's important that you finish graphing both lines to show that you've used this method. Once we've finished graphing both lines, we're going to identify the coordinates of the intersection point. The coordinates of the intersection point are 2 and 2, or 2 comma 2. And let's do a check. We always want to check in the original equations. Not the equations that we've solved for y, since we might have made a mistake in solving them for y. So my first equation is x minus 2y is equal to negative 2. I'll replace the x with 2 and the y with 2. And we'll see if the arithmetic works out. 2 minus 4 is equal to negative 2. That checks. The second equation was x plus y is equal to 4. I'll replace the x with 2 and the y with 2. And 2 plus 2 is 4, so that checks. Therefore, my solution to the system of equations is the ordered pair 2 comma 2, which means x is 2 and y is 2. All right, let's try another system. In this system, our two equations are x plus y is equal to 0 and x minus y is equal to 4. I'm going to solve each one for y so that we have the equation in y equals mx plus b form. So the first equation is y is equal to negative x. That has a y-intercept of 0 and a slope of negative 1. And we want to graph as many points as we can so that this is graphed accurately. And we'll connect the points to form a straight line. Our second equation is x minus y is equal to 4. I'll subtract x from both sides of that equation, giving us negative y is equal to negative x plus 4. We can then multiply or divide both sides of the equation by negative 1. And that will give us y is equal to x minus 4. So this equation has a y-intercept of negative 4 and a slope of 1. Again, we want to graph as many points as possible to create an accurate graph. Once we've graphed both lines, identify their intersection point. Their intersection point is the point 2 comma negative 2. We can check that in both equations. And again, I want to check it in the original equations. The first equation is x plus y is equal to 0. So if I replace x with 2 and y with negative 2, that gives us a true statement since negative 2 plus negative 2 is equal to 0. The second equation is x minus y is equal to 4. And again, replacing x with 2 and y with negative 2, we get 2 minus negative 2 is equal to 4. That's also true. So 2 comma negative 2 is the solution to our system of equations. In example 4, we have two lines to graph, the first of which is 2x minus y is equal to 1. I'll subtract 2x from both sides. That gives us negative y is equal to negative 2x plus 1. Dividing both sides by negative 1, the equation becomes y is equal to 2x minus 1. That has a y-intercept of negative 1 and a slope of 2. So we'll graph as many points as possible to have a very accurate graph. The second equation is 2x minus y is equal to 5. If I subtract 2x from both sides of that equation, we have negative y is equal to negative 2x plus 5. Dividing through by negative 1, we have y is equal to 2x minus 5. That graph has a y-intercept of negative 5 and a slope of 2. What you're going to notice about these two lines is that because they do have the same slope but different y-intercepts, they are parallel lines. So parallel lines, as you know, do not intersect. So we'll say that they have no intersection point. So what does that mean about the solution to this system of equations? This system has no solution, which we sometimes write with a symbol for the empty set because the lines are parallel. No intersection point means no solution. All right, let's take a look at another example. In this last example, x plus y is equal to 3 is one of the equations. Subtracting x from both sides, that gives us y is equal to negative x plus 3. That has a y-intercept of 3 and a slope of negative 1. So we'll want to graph as many points as we can to graph this accurately. And then the second equation is 2x plus 2y is equal to 6. I'll subtract off 2x from both sides, and we get 2y is equal to negative 2x plus 6. Dividing through by 2 on both sides, we'll get an equation that looks like y is equal to negative x plus 3. What you're going to notice about it is that it is the same line. So where do the two lines intersect? They intersect at every point on the line. So in this case, the two lines are actually the same line, and since they intersect at every point on the line, there are an infinite number of solutions. Be careful, the answer is not all real numbers. Why? Because every point is not necessarily on the line. So we just say that there are an infinite number of solutions. And that is our lesson for today.